Uh, so today my presentation topic will be logic in complexity series. Actually, there are lots of connection between mathematical logic and the computational complexity theory, especially the arithmetic and the complexity theory. So we shall present three theorems about this. The first one would be delta zero sets are essentially the same as linear hierarchy. So delta zero set is a class of definable subset of natural number, and which we will specify below. And the next one would be if I delta zero implies MDRP, then NP is the same as co-NP. So this one is implication in weak arithmetic. Will show that this will have some highly non-trivial consequence in complexity theory. And the third one is the relation between bounded arithmetic and the polynomial hierarchy. So first we shall introduce the arithmetical hierarchy, which is the classical object in mathematical logic and computability theory. So we will have a language of the first order arithmetic. So here the language is not the same as the language in the lecture. Here the language means a set of symbols. We have equality, plus, times, and less than 0 and 1. And the intended model would be the set of natural number n. So with these symbols, we can write down a lot of formulas to state some properties of the natural numbers. So for example, we can write there is y, 2y is equal to x. So we define this, we define this as formula phi x. We can see that this is just x is even. So this formula actually defines the set of even number in natural number. And next we shall classify these formulas in terms of their quantifier. So we say that the formula is delta zero if and only if all of its quantifiers are bounded, which means that it is in the form of there is x less than ty, where t is a term, such as phi xy, or for x less than ty phi xy. So here a term means t is a term. So for example, ty is, let's say, y squared plus 1. So a term basically means a polynomial. And next, we shall define sigma n formula. So we say that the formula is sigma n if and only if it is in this form, where phi is a delta zero formula, and it starts with a existential formula and with an alternate quantifier. And similarly, we can define a pi n formula, which is basically the same, but we start with a universal quantifier. And we say that the formula is delta n if and only if it is equivalent to both a sigma n formula and a pi n formula. And we add a subscript n to means that all the subset of natural number defined by the delta zero formula. So especially we can say that even number is inside delta zero definable subset. And similarly, we can define sigma n and pi n, and here is the arithmetical hierarchy. So delta zero definable subset is a subset of sigma 1 definable subset, and so on and so forth. So this is the arithmetical hierarchy. So actually, from the classical computability theory, we know that the delta 1 definable subset of natural number is exactly the same as computable sets. And there is a truth definition, sigma n truth definition formula for all sigma formula. So which means that there is a formula SAT such that SAT phi, where this means the code of phi, if and only if phi is true in natural number. So this is basically the same as the universal Turing machine. So using the diagonal method, the same as halting problem, we can show that the arithmetical hierarchy is strict, which means that sigma n definable subset is a proper subset of the set of sigma n definable subset is a proper subset of sigma n plus 1 definable subset, and sigma n is different from pi n. But the problem is if we want to consider like polynomial hierarchy, it is hard to define this truth definition formula below this delta 0. So we cannot do the same thing to prove that the polynomial hierarchy is strict. So actually, except this arithmetical hierarchy, all of the other hierarchy, especially lies very below delta 0. We do not know anything about this. We don't know whether it is strict, whether it will collapse or not. And the last thing is the arithmetical hierarchy is too coarse for the complexity theory. So as I just said, even the very low part, the delta 1 set, already contains almost every class in complexity theory. So we shall, how to say, we need to investigate more about what is lower than delta 1 or even delta 0. Okay, let us temporarily go back to complexity theory. So here is the linear time hierarchy. So it is completely parallel to polynomial hierarchy. So let's just quickly go through this. So we like this sigma 0 linear is all the language of which can be computable in linear time, and we have sigma n plus 1 linear. If we already define as sigma n linear, so sigma n plus 1 linear is all the language which can be computed by the non-deterministic linear time Turing machine with oracle in sigma n linear time. And pi n is the complement of sigma n, and the linear hierarchy is the union of all sigma n. And similar to the polynomial hierarchy, we can write down the formal description of sigma n sets, the sigma n language as follows in this form. So there is xn for xn minus 1, and inside this R is in linear time, and this all the quantifier would be in this form. So there is x such that the length of x is bounded by some linear term in parameter. So actually, we are going to show that linear hierarchy is the same as delta 0 definable subset. But here the problem is this one is a subset of 0, 1 star, while this one is a subset of no, shouldn't say so. I should say this one is the subset of a power set, and this one is a subset of the power set of natural number. But we can have a correspondence using the binary representation. So from now, we shall not distinguish natural number and its binary representation. So let's say we have a natural number x, x and its binary representation. Let's say it's 101101. So by this correspondence, we may view a subset of natural number the same as the subset of 0, 1 star. And here the length of x, when we view x as a binary string, would be roughly log x. And here log means log 2. So how we're going to show that linear hierarchy is actually the same as delta 0 definable subset. So here actually the quantifier part is the same. So here we can see that in definition of linear time hierarchy, all the quantifiers are in this form. So we must assume that the quantifier is like this. So there is x, the length of x is bounded by some linears in y. And if we take the exponential, so it becomes 2 to x less than c. It should be 2 to cy, which would be actually x less than the 6th power of y. And this one is roughly x less than ty. You can see the similarity here. So this is just the definition of boundary quantifier. So in the quantifier part, the linear hierarchy just resembles delta 0 formula in the higher level. So here we need to write a bit more. So this one would be a typical expression for linear hierarchy, and this one would be a typical expression for delta 0 definable subset. And this R is in linear time, and this P is something without any quantifier. So we want to prove that these two things are the same. We want to show that this R is actually in delta 0, and this P is in linear hierarchy, right? Because we know that the boundary quantifier outside is just the same. Okay, so we need to show that linear time is delta 0 definable, and sets without quantifier are in linear hierarchy. Okay, we first deal with the first part, which means that the linear time is a subset of delta 0 definable subset. So the idea is quite simple. We have a Turing machine M, which runs in linear time. We want to describe its computation with a delta 0 formula. And how are we going to do this? We record the computation of each step, and the total amount of steps is bounded by some linear function of the input. So we may write there's a S. S is a sequence of steps. So the length of S is bounded by some linear term of the input X, such that S is sequence of computation. But here the problem is we cannot record the global configuration of each step. Instead, we can only record the local configuration, which means the current state of head and the symbol on the tape near the head, and the operation it takes. So what we record is something like this. So we have 0, 1, 0, and the head is here, which is in state A. And let's say the operation is move right. So it will be 0, 1, 0. So the head is here with state B. So we can record this local configuration. But the point is, the global information can be computed inside. So all we need to do is to verify that each step is a legal step with respect to the Turing machine M. But here, the Turing machine M is fixed, so we have only finitely many local configurations and finitely many transitions. So we can write down all the transitions. So we may write it out. So we may write the delta formula, the delta zero formula like this. Like there is S length x is bounded by some linear term of x, and this is the same as S is less than some polynomial term in x. S is a sequence. S is sequence, and the length of x. And for any I less than the length of s, Si to Si plus 1 is legal with input x. And S0 is the initial state. And as length s is terminate. So since there are only finitely many transitions, so we can verify this thing. So the transition from the configuration Si to Si plus 1 with input x is legal. We can verify this using a delta zero formula. So all the things we can see that all the bounded quantifier here and here are bounded. So this can be done in the delta zero formula. So this is one side, although it is not that accurate, but I think here is a strategy. Okay, so let's see the other side. So here I write it as a verifying polynomial equation. So actually we can see that if a formula is without any quantifier, it will be look like px is greater than or equal 0 and or qx is equal to 0 and something else, maybe with some bracket. Because all the connectives can be easily computed in linear hierarchy. So what we need to do is to show that these predicates can be computed or verified inside a linear hierarchy. So in particular, we shall show that the graph of plus times and less than equality can be verified in, we shall do this in two steps. First, we verify that these things are in log space. And the second thing is log space is a subset of linear hierarchy. So for these two relations, they can be obviously verified in log space. So the idea is quite simple. So let's say we have a 10111 is the same as 10101. We want to check whether this is true. And here the input. So the first thing is we record the length of the input, which need a log space. So here the length would be 5. So what would we do next? We compute for each entry less than 5 here. So we check that whether if here is 1, then here must be 1. Whether the two entries are the same. Here's 1, here's 1, it's okay. Here's 0, here's 0. But for here's 1, here's 0. Then we conclude that these two strings are not the same. So this computation will need log space. And also for plus and times, we can do the computation in high school style. But here we, instead of using the decimal representation, we use the binary representation. So let's give an example. We want to compute 1011 plus, let's say 101 is 0 1 1 1, let's say. We want to verify that whether this is correct or not. So what we do, the first thing is again we record the length of the input, which need block space. So the length of the input would be that's 4 and 3. And next the point is we compute for each entry. We verify entry by entry whether the result is the same. So let's say here we first compute this one. So 1 plus 1 is 0. So this entry is correct. And next, we need additional space for the carrier. So there's carry 1. We record the 1 here. And next, we compute this row. So this row would be 1 plus 1. 1 plus 1, which would be 0, but here is 1. So we know that the computation is wrong. So here we need log space for this computation, for this high school style computation. And similarly, we can do multiplication. So let's say 1011. Let's say this here is 1 1. Again, we do this in high school style, but we still do it entry by entry. So we first want to compute this entry. So here the first thing would be this part, right? It will be 1011. But instead of computing the global results, this will need a linear space, but we do not have linear space. We only have log space, so we cannot do this. Instead of this, we only compute this one, right? And next we compute the next row, 1011, but we only record this thing. And fortunately, here's nothing, and we know that the result is 1, and we compare it to the given result whether it's correct, and we keep doing things like this. So this is a strategy we use to to show that the graph of plus times and less than equality, it can be verified in log space. Okay, next we need another class and a theorem called Nepean-Jasicki theorem. I don't know how to pronounce it. Okay, we say that the Turing machine is in time space Fg if and only if M use time in Fn and space in Gn. But notice that this is not the same as the intersection of time bound and space bound. This is a bit smaller in general. And the theorem says that if epsilon is less than 1 and alpha is an integer greater than 1, then this time space class is inside linear hierarchy. So we shall prove that this one is in linear hierarchy by induction on K. So for K equals 1, it is time. It is inside time n1 minus epsilon. So it is a subset of linear time. So for base case, this is true. And suppose this holds for K, and we want to prove the same thing for K plus 1. So we start with a Turing machine M in this time space. So we want to construct the oracle non-deterministic Turing machine K, which output the same as M, with some oracle in the last level, in this level. So how are we going to construct this? So we claim that K accept if and only if there is a list of n to the 1 minus epsilon plus 1 many configuration of M. So here the configuration means global configuration. So we record all the information in all the tapes and the position of the head, such that the first configuration is the initial state and the last configuration is the terminal state. And the most important thing is for any two consecutive configuration in list, the second one can be reached from the first one in n to the k times 1 minus epsilon many times. So it's something like if we can compute within k nk plus 1 times 1 minus epsilon 20 times. So there is nk plus 1 minus epsilon many times. So we can write it as, we start with the initial, and here to A1 to A2 to an to 1 minus epsilon, maybe plus 1. And between each two consecutive configuration, this needs, here we need nk 1 minus epsilon many steps. Not need, at most. In M. And there are two crucial points. So the first one is the length of this list. So since M used space in n epsilon, so the length above is bounded by n epsilon. So So for each configuration, the amount of space it takes is almost unoptional uh, up to some constant. So here is n epsilon times n y minus epsilon, which is linear n. And the second thing is the second requirement. It can be computed in this time space by just simulate m. And after this many steps, we just terminate. This can be computed in this time space hierarchy. So by induction, this computation is in linear hierarchy. So K is a non-deterministic linear time Turing machine with the oracle with this computation. This computation is in linear hierarchy means that this computation is in sigma n linear for some n. So this K or M is also in linear hierarchy. Oh, sorry, I forgot to mention that there's one last step. So here, obviously, log space is a subset of time space